So heads up, today's going to be a difficult one, just so you know. It's not the easiest subject of what we're diving into. I've tried to make it as simple as possible, but feel free to stop me if it's not. All right, everyone, my name's Nat. It's Thursday, and that means it's webinar time, where we dive in deep on a subject related to neurodiversity, neuroscience, cognitive functioning, how our brains are put together, and why they work, and also why they don't always work. While we're talking about Parkinson's, which you might think, but nah, that's not neurodivergence. Well, no, it's not. But it's very closely related to ADHD, which a lot of people don't realize in terms of what's going on in the brain. Once again, it's bloody dopamine. And we're going to be looking at more about dopamine and why a slight little change can have big effects. So as we said, having a mental health condition and being neurodivergent, they're not the same thing, but there is a lot of overlap. And that is one of the reasons why we're diving in deep on this session today. Today, we are not talking about dyslexia, we're not talking about dyspraxia, autism, maybe a little bit ADHD, but we are going to be going into a completely new area, and it's just because it's quite interesting how it does relate to our pathways. Here's our team. Most of you know it by now. I won't bore you. You can look at our faces if you like. And in terms of our last webinar, which was a roaring success, even if I do say so myself, we did autism and we explored cognitive functions of ASD. Essentially, what do we mean by cognitive functions, executive functions? We looked at how different brains have kind of top-up processing and bottom-down processes, and how different ways equal different outcomes. Such as this image, is it a woman or is it a guy playing the saxophone? Well, depending on how your brain is wired, one may see one image faster than they see the other one, or you might not be able to see the other image at all. So Parkinson's, dopamine, and the brain. Now, they have to go hand in hand because Parkinson's and dopamine, it's sometimes when the brain isn't sending the right chemicals. Sometimes you might get too many chemicals and you get a different diagnosis. Other times you might get too many and you get a different diagnosis. So the brain is a fragile thing. It can do with a little bit of variation, but too much of a good thing is a bad thing. And that is what we're going to be exploring today. Now, Parkinson's, I could go in, today's session isn't about learning about the characteristics, the symptoms. It isn't about learning how to support people with Parkinson's. One, that's not my area of expertise. And also, I think there's that kind of information already online. Today, we're going to be looking at what's going on under the hood. Why is the brain acting the way it is? And potentially we can do something about that. Oh, and it just says, I read something about ADHDers on average are more likely to get Parkinson's, but not sure if this is supported with studies. Well, I think it might be, to be honest, because as we go through today, you will see how it links. When dopamine and ADHD highly linked, Parkinson's and dopamine highly linked. So it's not a far stretch to see, or at very least, a lot of the same characteristics and a lot of the symptoms might overlap. But obviously there is a difference, and we will, fingers crossed, get into that today. Now, I'm going to start off with a question to all of you, and this is a hard one, really. What is Parkinson's? Now, maybe some of you might have personal experience, and if you do, please share if you feel comfortable to. Maybe you just have a rough idea what you've seen on the news. Don't worry about getting this answer right. I just want to know what you currently think it is, and then we can start breaking down stigma and start hopefully explaining it in a really accessible way. And also, if some of you have no idea what Parkinson's is, tell me you have no idea. That is also a valid answer. All right, we've got a neurological condition that affects the brain, presenting with many physical symptoms, including tremors and dementia-like deficits. I feel like you went on Google and got that, but it's good. No, all right, that is a good definition. We've got a disorder of the nervous system. Very good. We've got starting to learn about the functional neurology. All right, well, we'll leave it as that because I appreciate some people might be like, I'm not sure. Oh, Mary says a disease of the brain that you get tremors with. My brother-in-law has Parkinson's. Oh, thanks for sharing that, Mary. Oh, Emma's interested in the condition as it runs in the family. Definitely worth knowing more about, because a lot of the time you won't realize it until it's quite far developed. With all things, catching stuff early means support processes are good. Is it something to do with damaged neural pathways? Yes, absolutely it is. Essentially, how I would summarize Parkinson's, it's like the traffic lights at a junction are not working right. When it's go green, you're meant to go, but with Parkinson's, it's red, but you're going anyway. So like the lights aren't really working effectively. So thankfully, most of you are on the same page, which means we can go a bit deeper. So the National Institute of Aging says Parkinson's is a disease in the brain disorder that causes unintended or uncontrollable movements such as shaking, stiffness, and difficulties with balance and coordination. Symptoms usually gradually and worsen over time. I don't know if you know any famous examples of individuals with Parkinson's, but isn't Marty McFly? Yeah. So okay, someone help me out. Name?
Yes. Michael J. Fox.
Yes, thank you. Michael J. Fox. I think he's a really interesting example because you can see how he has progressively gotten worse over time to the point where he struggles to like write down, even chew, even like talk. And there's lots of devices and support strategies which are able to help people. There are like special forks which keep you from shaking or allow you to get the food in your mouth. So it really can affect all parts of your body. It's around movement. So, if there's not a right regulation of dopamine, you're not able to control your movement as effectively. And as that gets worse, hence. But remember, also, you can see how it parallels with ADHD, which is hopefully a comparison we're going to keep drawing from today. Yes, April, Ozzy Osbourne, who is the thumbnail of today's webinar, has Parkinson's. And interestingly, I think he's still touring and doing music. So for some of us, it doesn't happen straight away. It can be a very slow process. Now, this little image here shows you some of the characteristics. So you can have stiffness, you can have pain, reduced arm swing, tremors, fatigue. It can even affect urinary tracts, dry skin. It can make you more likely to fall. It can have problems with your sleep, depression, memory problems. It really is not a great disease to have, and it can affect all of you. But like I said, it affects people differently, and the early stages might seem just like a normal part of the human condition. So the sooner you're able to catch it, the sooner you're able to get support. Now that we know what neurological Parkinson's is on a top level, we're going to go deeper. And this is where hopefully we'll get some content which you may not already know before. And heads up, today is a bit challenging, and I have tried to simplify it as much as possible. So please bear with me. If something doesn't make sense, I will keep checking in and keep doing summaries. So first of all, we need to know about the old brain, the basal ganglia. Where is it? Any of you know where the basal ganglia are? If you do, you put a little pin on the brain. Brilliant. And if you have no idea, don't worry about it. We will teach you. But this is going to be the key area when it comes to Parkinson's and looking into the brain. So in short, the basal ganglia is deep in the brain. Imagine it like a bundle of different areas working together. Some of these areas are called chordae, nucleus, putamen, globus. Read it yourself. But essentially, lots of different areas in the brain clumped together is the basal ganglia. Okay, a lot of you have already put it in the same area. Now, it could be. It's kind of like deep in the brain, to be honest. It's in like kind of the middle bit. I will show more detailed information momentarily, but it is here. So this is the basal ganglia. And as I said, it's made up of different parts. And all of these different things are key areas that we need to be mindful of, because it only takes one of them to not work hunky-dory for disaster to strike. So we are going to be looking at these, and all of these together combined with motor control. Now, as a lot of you will know, dyspraxia, which is also another developmental condition, also relates to motor control. So you can see how these things, none of them are that dissimilar. What makes someone have ADHD to dyspraxia to Parkinson's? Sometimes it can be very small difference. Some of us, I suppose, get lucky, others not so lucky, if you could even put it down to categories like that. So the basal ganglia, or BG as its friends like to call it, essentially is filled of nuclei, and these are like lots of little cells that are working together as a team. When you look at the basal ganglia from the side, you can see these areas. So this is it from the side, essentially chop the brain in half, and then you can kind of see what it looks like. But it really is deep down in the brain. It's a very old part of the brain in terms of an evolutionary perspective. Two of these areas, the caudate nuclei and the putamen, work closely together and are called the striatum. So that's another important thing to know. Striatum, that's a term we're going to be using a lot today. And okay, so this bit here, striatum, the whole thing in itself is the basal ganglia. Names I don't think are overly important, but it's to know roughly kind of what regions we are going to be focusing on today. Now, if we were to cut the brain up even more, slicey dicey, we're going to be able to see a bit more clearly exactly what's going on. So this is a side view that we've already seen before. But if we start to slice the brain up like a bit of ham, you'll see that it's split up into little sections. So the striatum is the bits in purple. And this is an area we're going to be focused on quite a lot lately. So as you can see here, that is the real big chunk of it. That's like the majority. Then you have like the STN, which is red, which is a little sliver, GPE, and SN. Now, again, in terms of exactly what these are, I don't think you need to worry about in too much detail, but just know that the difficulty is when these areas are talking to each other. So all of these areas together, the basal ganglia, are super, super important when it comes to movement. Now, if one thing isn't talking to the other thing, then we've got difficulties. So this is like a team project when you all have to work together. In an ideal world, it works great, but sometimes someone's not pulling their weight and the whole team collapses. So all of these areas have to talk well together. Now, in terms of how these areas talk together, you could think of it like a team meeting, like people having a chat, or kind of like a flow diagram. So things all flow together in a nice little pattern. And in an ideal world, the cortex talks to the striatum will talk, go to the STM, will go to the thalamus. Things are all talking to each other. So on the left, you can see it kind of overlapping on an image of the brain. And on the right, you can see like a diagram. This is what they normally use in like science documentaries and books. And the lines, they show the pathways. And all the pathway is, think of it like a highway of chemicals. So when our brain is sending chemicals, there's these pathways like tubes. So yeah, the red one is your glutamate. That's an interesting chemical. We're not really thinking about that today. Then we've got a bit of GABA, and all these are neurotransmitters. These are essentially chemicals that tell the brain what to do. Now, it's the orange line on what we need to really focus on. This is the flow of dopamine. And you can see sometimes it goes in one direction, but it doesn't go backwards. Anyway, so as you can see, all of it is connected, and they're all connected via chemicals. Now, if one of these chemicals aren't working, not great. But remember how I said at the very start, think of it like kind of traffic lights. When the green light says go, chemicals are flowing. When the light's red, no, chemicals aren't going. But if this light is on the blink, then you're going to have traffic jams, you're going to have car crashes, it's going to be a right horror show. And this is kind of what's happening in someone who has Parkinson syndrome. Another way you can look about it is kind of loops. So remember how we talked about highways? And think about like different kind of loops and circuits have different highways. You know, those like Pescetti junctions, which kind of look ridiculous, where the cars are going in every direction. That's kind of like what's happening in the brain in the basal ganglia. So here you can see again the basal ganglia, the different colors show the different parts that make up the collective. And here, all these different lines are different roadways, different motorways, pathways, through roads, A roads. So you've got the motor circuit, associated circuit, limbic circuit. It sounds like an episode of Mario Kart. There's lots of different routes to go on. And each one has its own kind of role and function in the brain. We've talked about these before in kind of different kind of scenarios. Dopamine loves traveling down these areas, but also, like I said, you can get glutamate, you can get GABA. Lots of different chemicals can take advantage of them, but some more predominantly than others. All right, so have a look at this little diagram here, and I appreciate, it looks a bit technical, but it's not that complicated, really. It's just a really simplistic way of looking at the brain. You've got the cortex, then the striatum, and remember, like, the green is excitatory connections, so go, 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 green light, and the red is red light, do not go. So I want you to have a look at here and think, how many connections does the striatum have to the eye? Remember, what they actually are maybe aren't so important. It's more of the idea behind it. Okay, oh, 2, yeah, 100%. That is correct. So here, cortex, right? The green, go, go, go. So, okay, striatum, nice, we made it to the striatum. Now we want to go to the GPI and the SNR. Okay, direct route. Nice and simple, not messing about here. But if this route is not working, we can go an indirect route, and we can go up through the GPE, STN, then we get there. So there's 2 routes to get there. And one is nice and efficient, the other one, not so much, but you do get there eventually. So that's another important thing to know. There's multiple ways in order to get to one area, normally. Now we're going to focus a bit more on movement, and we'll break it down. So we talked about these connections: green light, go; red light, do not go. And the basal ganglia, that is needed for movement. So movement connections. If we see the green light, go; red light, do not go. It really is very similar to traffic lights. The cortex has excitatory inputs to the striatum. So when we talk about excitaria, sorry, just, sometimes I really get tongue twisted. All we mean is that's a go light. And if we talk about inhibitory, we're saying no, do not go. So though we're using complicated words, they're really meaning very simple things. When can we go? When can we not go? But the important thing is the output nuclei inhibits the thalamus. So things can't talk to each other if we don't have the green light. So as you can see here, we've got the cerebral cortex, part of the brain. Then, okay, we've got to go to the striatum. Oh, and then, oh, God, bugger, the light's off. We can't go this way. So if this isn't working, we can't complete a full circuit. And again, bad times, it's not working well. As I've said before, if you're not following, hold tight, because hopefully it will all start to fit into place as we go along. So in a kind of real top overview, the basal ganglia helps us move by controlling our go and stop sign. This is kind of like TfL. These are the people who control all the roadways around London, maybe. And if they're doing a good job, business as usual, the trains are working nicely. If they're not, we're not going anywhere. So again, stop light is no-go. Suppressed activity in the region means things are going to go slower. You might, in a traffic jam, sometimes there's no traffic, sometimes it's slower traffic. It can really pause it. So if we think in Parkinson's, how people stutter a bit, it's a real slowdown of that information. In your head, you're like, yeah, I want to move. I want to put this fork in my mouth and eat my cereal. No, we'll say spoon. We want to put the spoon in my mouth and eat the cereal. Nice. But if there's a bit of a delay, it's a bit jaggedy, and the message just isn't getting there. If we have decreased firing, all we mean by that is, when we talked about where chemicals go from one part, like whoop, to the next one, if the kind of like chemical from one neuron to the next neuron is a bit slower, then we're getting that red stoplight. We really need a nice constant flow of these beautiful brain chemicals, these neurotransmitters, for everything to work in harmony. And yep, the other stuff is just a basic overview. So just a real quick check-in. How much of this are you following? Is it like, yep, you don't understand? challenging, but you're kind of getting the gist of it, or you understand it well. Okay, challenging but good. All right, that is a good place to be in. If any of you were understanding it well, maybe this wouldn't be the right session for you. If you didn't understand it, well, I could obviously break it down further, but like I said, it is challenging. So I'm glad that we're all on the same page. Now we're going to look a bit more deeper into pathways. So we've talked about the kind of areas of the brain. Again, we've got the thalamus, the striatum, the like you can see all these areas, but how are they all connected? And they're connected via pathways. So as you can see these lines, like you've got direct pathways, which are like the motorways. They've got like the old country roads, which have to stop at multiple different stops along the way. You get some pathways which are only for certain chemicals, maybe only for large trucks. Some pathways only taxis and buses can go on. So all of these roads have different functions. Some are for certain types of vehicles. Others are for like ones that are sharing passengers. Others are for large vehicles. Others for like small, like horse and cart. So they all have different functions. And depending on which one's working and which one's not, will often depict the kind of characteristics that you get. Remember, there's two types of pathways. We've got direct and indirect. So motorway and local urban road, which probably has potholes. So looking at these two images, I want you to see if you can work out which one is the direct pathway, which one gets you there nice and quick. So the direct pathway on the basal ganglia circuit for movement. Okay, we've got one answer in. Nice. So far, 100% of you, which I think is 2 people. Oh, thanks, Jennifer. You says A as well. It is A, yeah. So we can see here, it's a very direct pathway from the thalamus to the cortex. It's going around, nice and simple. But if you can see on number B, XXX, this road has been shut down and now it has to go a different route. So this is by far not a direct pathway and not the kind of ideal route. So again, you might not understand the images fully, but it's quite clear one is going well, one is not. So one's a green light, one's a red light. So a direct pathway, like trying to do it as simple as possible. We're going to be, let's break it down. So let's start at the thalamus. So we've got excitatory projections. So this is the movement. When you think, yep, I'm going to move my arm. Go, go, go. They're in the cortex. Yep, still excitatory. We've still got green light. Go, go, go. Now in the striatum. And that's when you get inhibition. You can't move. And you can see how like the circuit doesn't quite kind of work. So at some point it's nice and fast and then it slows down. Now, if this is a direct pathway, what is an indirect pathway? So as you can see here, the thalamus isn't talking to the cerebral cortex. Different routes have been blocked. So let's say we want to take an indirect route, striatum there. Oh, we can't go. This has been blocked off. So we can only go one way. So rather than having multiple routes in order to get to the same place, you have to take the route, the only one that is on offer. Oh, Jennifer says, is this the same effect for non-motor Parkinson's like Lewy body? Well, I'm not that familiar with that one, but yes, it would be. This circuit relates to just how all of us work and move. It's only when certain areas are functioning less well or not as intended where you might get certain conditions, say like Parkinson's. But this is like the basic format for everyone. We all have direct and indirect pathways, but sometimes they don't work as effectively as we would like. So in a quick summary, the basal ganglia is important for mental health. Essentially, a good basal ganglia, hopefully good mental health, because it means the chemicals in your brain are actually doing their job. If you want your dopamine, the brain's given the dopamine. If you want some GABA, you get the GABA. You know, glutamate, you get your glutamate. So really important for mental health. Then there's 2 pathways. You've got your direct ones, superhighway, and your indirect. A bit of a slower route, but still does the job, still gets there. And these 2 pathways help control how we move. Because if it was always green light, you never stop moving. You have to go like on, off, and this allows us to control. In our brains, we feel like when I'm moving, I'm just moving, but our brain is doing so many actions like, okay, now move the arm, stop the arm, reactions, motor coordination, playing video games, riding a bike, doing up your buttons, doing your shoelaces. This is super important. And if these things aren't working correctly, you'd be terrible at video games. You might already be. I know I am. You might struggle riding a bike. It might take longer to cycle. Anything which requires you to be able to start at an appropriate time is going to be impacted. And Parkinson's, as you'll notice, when you're starting off, it's just a little bit of jittery here and there. But as the condition worsens, you'll notice that people become less and less likely to move. So if we're looking at this analogy of a traffic light, if it's already blinking on a bit and no one's fixing it, it's only going to get worse and worse as time goes on. It's not going to be fixing itself. So all of this is super important in brain disorders. And notice we say brain disorders, not just Parkinson's. There's research is still needed, but you can see a lot of overlap already in things like ADHD, Parkinson's, maybe dyspraxia. We are still very much in the early stages of understanding what's all happening, but we do know this much at least. So yeah, emerging field and all subject to change, but there's lots of studies and research on it. Let's look a little bit further at our friend dopamine. And we've mentioned before, dopamine is a neurotransmitter. All that means is it's a chemical in the brain which allows your neuron, your brain cell, to talk to the next neuron. You've got one cable, then you've got a gap and another cable, and a chemical that flows in between the two cables, that could be a chemical such as dopamine. Dopamine is essential. We often talk about it being like a feel-good chemical, but it's not just about happy feelings. It can also help with movement, just normal function. It's a complex little chemical. It does a lot in the body. So here is a little reminder about what these chemicals actually are. So we've got the neuron, which is a brain cell. And at the end of the brain cell, we've got the synapse. And you've got this little synaptic cleft, which is that gap I just spoken about. And then we've got the next neuron. So as you can see, these little kind of red dots for this document, let's say they're dopamine, when the body gets a jolt of electricity, like, yep, you should probably move now, it sends it. It gets so much energy that it kind of shoots out. It's floating in the abyss, in the synaptic cleft. And then the receptors, which are these big kind of gloves, catch onto these dopamine or chemicals and pull it in. This is what a very healthy body looks like. You can also, like when we get like too many, the body will also do a nice bit of recycling and suck up the leftovers, and the process can repeat. So this is a nice, healthy, working example of the brain talking to other parts of the brain. And we have millions and millions of these little cells in our brain. There are a lot of them. So dopamine as a modulator of the pathways. We're looking at this kind of diagram again. We've looked at it before, but now we're going to look at it under the lens of dopamine. So the green is dopamine kind of going around, and you've got D1, D2. These are different types of receptors. And remember, when we talk about receptors, we're talking about these big gloves that kind of catch the chemicals and draw it in. So receptors are needed in order to capture the dopamine. Direct pathways has D1 receptors. So D1 would be like the name of like the express route. And indirect pathways are D2. These are the slower route. Both are very useful, but different functions. Dopamine affects these pathways differently due to those receptors. So depending on what's working, what isn't, we're going to have different outputs. So hopefully that all makes sense. This is a big roadmap of a part of our brain, and dopamine is kind of sending the connections one to the other, to the other, to the other. Now, if you're thinking, this seems like a lot of information, I really can't be bothered to like absorb this right now, don't worry, I've got you covered. Indirect pathways suppress action, direct pathways facilitate action. So indirect, red light, direct, green light. I think that's pretty simple. It kind of helps us going. So as you can see, one is one route, one is the other route. So D2 lowers activity in the indirect route. So D2, when this one is working, it's kind of slowing things down, like, whoa, let's not send this chemical. It increases activity in the direct pathway. So when D2, another way of looking at this actually is, you know, when you got your taps on, if you got both like hot and cold tap working, they're both flowing, but slower. But when you turn, say, the hot tap off, the cold tap starts faster. And this is very similar to this. So when the D2 tap is kind of turned off, the D1 will start flowing faster and vice versa. So sometimes you can modulate the other one by changing the one, like D2. So D1 influences D2, D2 influences D1. And together, turning taps on and off, allowing traffic to flow left and right, fast and not, the traffic lights, whatever analogy you want to use, this equates to movement. And D1 does the exact same, but in the opposite way. So as I said, both very useful. They work in harmony together to kind of coordinate the flow of information / traffic in our brain. Now, here is a real example of how we actually know this stuff to be true. So here is a little fuzzy critter, poor thing, and this highlights the importance of these pathways. So we've got the activation of indirect pathways suppress the inhibition motor behavior. All this means is, in this rat, you can see there's a little kind of like a thing in its head there, and they've been able to activate the indirect pathways. So the light which says do not go, they've been able to turn on. And as you can see, the rat is only, or maybe it's a mouse, I'm not sure, I think it's a mouse, it's only able to go left and it's not able to go right. So you can see its movements aren't quite functioning. So when they have artificially stopped these pathways from working as they're supposed to, we can visually see that the movement isn't working great either. So this is real evidence that these pathways genuinely do have an impact on our movement. Now, I don't know, maybe you think this is unethical or not. I mean, it's one of those kind of necessary evils in order to like study. Now, we share a lot of common DNA with mice, so they're quite a good model when it comes to testing these areas out. Now, let's look a bit at dysfunction. So we've talked about how things should work. Now let's look at how when they do not work. So the basal ganglia, again, it's at the center of this discussion. And if it's not working, this is when we might run into like conditions such as Parkinson's. So the basal ganglia, if it isn't working right, if the dopamine isn't flowing, if things just aren't working as you would expect, you're going to run into motor difficulties. You're going to run into memory difficulties, attention difficulties, attentive difficulty, sleep. And what do you know it? All of these difficulties really overlap with neurodivergence. A lot of them sound a lot like ADHD, don't they? Like attention, deficit, being effective, sleep, memory, motor, dyspraxia. They're really, really similar. So when you think, Parkinson's, ADHD, are they really that similar? Well, when you get right to it, you can notice that they affect a lot of the same areas. So there are issues seen in like Parkinson's, Huntington's, and ADHD. So a lot of overlap in these conditions. Now, out of these other conditions which are affected by the basal ganglia, which ones have you heard of or most familiar with? So you'll notice like things like autism, dyslexia aren't there, but other ones such as ADHD, schizophrenia, obsessive compulsive disorder, Tourette syndrome are all there. So a group of conditions that symptoms a person feels and relates. So all of these are related to what we've been talking about. Okay, I can see only one person voted. Oh, 2, 3. Nice to come in. ADHD. Yeah, ADHD. Now that is what we talk about all the time. Now we also talk about Tourette's every now and then, and OCD being highly related, as well as schizophrenia. But poor Parkinson's doesn't get the attention that it needs. And actually, you could group these all together. You know, things get quite difficult. Are we talking about learning disabilities? Are we talking about neurodevelopmental conditions or neurodiversities or neurodivergence? Depending how you group them up, some conditions make the cut and others do not. I think this is why we don't often talk about conditions such as Parkinson's, because it doesn't quite fit in the category of, say, neurodevelopmental or neurodivergent. Oh, Jennifer says, myself and our 3 kids have ADHD and ADD. Oh, good to know. Thanks for sharing. Oh, Parkinson's dementia. Well, thank you for sharing. It is interesting how things overlap. Now, whether or not one to another one, I don't know, and I don't think so, to be honest. But it is interesting how if just things worked slightly bit different in your brain, something completely different may happen as a result. So let's have a little bit look at Parkinson's. We mentioned it at the start, and all of you kind of got it right. But the real 101 of Parkinson's is that it can result in tremors. This is when your movement is a bit jagged. You're not able to control the off and on. Like normally when you move your hand up, it stops. And that's quite a natural process. But if you're kind of like driving and you'll keep playing on the brakes, you know, like the brakes, your car's going to stutter. Very similar to the brain. It normally is when there's the dopamine in your body isn't being regulated. So often treatment which can support Parkinson's result is normally highly related to dopamine. You can also see that your Nigeria, like a part of your brain starts to diminish. So it's like part of your brain is kind of being starved of dopamine and it starts to kind of decrease and kind of shrink. And we talked a bit about how one neuron talks to the other neuron via chemicals. You'll see here that these chemicals, which are normally dopamine that fire from one to the other, start to get a bit, they start like slacking off. They're not doing their job properly. They'll get less chemicals. So if the brain is saying, hey, do this super fast, the super fast part of the message is getting completely lost. And all the brain is receiving is do this at your own pace. So it's when communication isn't working and the person who should be doing the communication is dopamine, but dopamine isn't pulling its weight. Here is an image of what we've been looking at already. And you'll see one is a normal, healthy way of working that we've already looked at. And you see these arrows, how information flows in the brain and the different chemicals. But with Parkinson's, if you try and follow the same patterns, you'll notice, there's less arrows. Things aren't connecting up as well as you would want. It's not a great image, but as you can see, the kind of like lined one is dopamine. And in a healthy brain, the dopamine pathways are connecting up to the D1, which we spoke about, the direct pathways, and the D2, the indirect pathways. But in Parkinson's, there isn't any direct pathways. The super expressway in order to get to A to B is, well, it's pretty non-existent. It's a bit, maintenance is definitely needed. So now the brain only can do off. It can't really do on. Or another way of looking at it, when there's everyone knows a part in their like local area where the traffic lights go green for like 1 second and then it's red for like 10 minutes. That is Parkinson's. Really annoying. It's like, why can't you have the green light on for just a little bit longer? The on and off, they don't make much sense. It feels like it's rigged. And that is very much Parkinson's. So on here, we've had a little look at the brain and we've taken some images. Have a guess at which one you think potentially might be Parkinson's. And the different colors just represent activity in the brain. So where the brain is most active and where it is not most active. Oh, Jennifer says B. We've also got a B on here as well. Any other takers? Okay, oh, we've got one person says A. Oh, 2 have gone for A now. B. A. Oh, okay, well, interesting. It's saying A and B, but it's definitely A. But if you can see here, there's less activation. If there's less activation, it's an example of Parkinson's because the dopamine isn't flowing. Now maybe C, but I think that might be wrong to be honest. So scratch that. But let's go for A. So in Parkinson's, the connection between substantial Nigeria and the striatum is lost. So connection A to B isn't working, meaning dopamine can't reach where it's needed to the brain. So number A, forget about C. It's A, where there is less activation. A and C are right, okay? And this is why. So we've got healthy brain. As you can see, the colors are very vibrant. They are very consistent. Then we've got Parkinson's disease before symptoms, so the early stages. If you catch Parkinson's early, you'll notice that things are starting to get a bit more fainter. They're still working, they're just not there. But then once Parkinson's has really kicked in, you'll notice that there is no activation or very, very little. B is when there is no Parkinson's. A is when Parkinson's has already been fully established. And C is when Parkinson's is often currently not recognized, but in the early stages. So the brain can tell you quite easily if you have Parkinson's or not, but it's only if you kind of get checked up early, which is when you might be able to do something in advance. Let's look at true or false. Direct pathways become more active or indirect pathways become more active. Which one is true? Which one's false? If you can kind of remember what we spoke about. So direct pathways, do they become more active or less? Okay, so it is indirect pathways become more active with Parkinson's. So just to really hit home, when you have Parkinson's, your direct pathways become less active and less effective. And just like we talked about that tap analogy, if we're turning one tap off, the other tap tends to flow stronger. And that, in a nutshell, is Parkinson's. So if you do not have dopamine or less dopamine, depending on what stage you are, less activity in direct pathways equal more activity in indirect pathways. Ideally, you'd have an equal flow of off, on, but if you have more off, then you aren't going to get those messages delivered effectively. Direct and indirect pathways help control movement. Does that make sense to everyone? I know we've been on a bit of a journey to get here, but this really puts it down into a nutshell. If our direct pathways are working and our indirect pathways are working, all good. If one is kind of being turned off, then the other gets more attention, but too much attention isn't great. And that also all relates to movement. Now, this is kind of reached the end on what we're mainly talking about today. I don't want to, well, maybe I already went overboard. I didn't want to go any more overboard because it's a complex subject. Now, mainly we talk about neurodivergence, but I wanted to know if any of you would be interested in kind of diving deep into any other kind of areas which kind of overlap with the basal ganglia and kind of coordination and motor conditions, such as Huntington's disease, dystonia, ambulia, pronounce that wrong, dementia or depression. Okay, we've got dementia and depression. I mean, like I said, today's session was a bit of a unique one just because there's a connection, but if there is interest, we will definitely kind of like overlap. Because as we're learning, being neurodivergent is as simple as being diagnosed with one condition. It's much more complex than that. And it's looking about all the co-occurring comorbidities that our brain has and the likelihood of having one and having another. Some quick bonus facts, just because I think that's quite interesting, is understanding free will. And this kind of relates to Parkinson's because you have to question, if we're not able to move, do we have free will? And if we are able to move, is that our choice allowing us to move, or is it the chemicals allowing us to move? When you start going in deep into this kind of way of thinking, you start to really question how much control we even have to begin with. So is free will expressed by our freedom to do what we want? Yes or no? This is just a bonus question because I thought it was quite interesting to kind of ponder it. And particularly, we got this, remember this mouse that wasn't able to choose how it moved. It could only move in one direction. That choice was already made for it. Okay, we got free will is expressed by our freedom to do what we want. Yes and no. Honestly, it's a really complex question. I think we like to feel that we have free will, but the more we learn about neuroscience, the less free will tends to be a thing. So just some food for thought. A nice quote from Kant, who's a philosopher from back in the day. He says, a person acts freely if he does of his own accord what must be done. Interesting. So what must be done? I would say that's like, breathing, these are all things which must be done. So maybe the fact that we can operate in a way which is required for our existence as free will, and free will isn't having complete choice over it. It's just doing what is necessary. Who knows? Interesting kind of thought. And we got a question to think about. What is free will, and has it anything to do with the basal ganglia? So when we're kind of searching deep for meaning on what it's to be a human being, maybe we don't need to think as theoretical, and actually it's more related to just the brain. Here are some lovely examples of research that was done for this session. A really complex one, I may say, and definitely out of my comfort zone, but I've really enjoyed researching it and trying to find a bit more about how the brain focuses. Out of all these books, I recommend 2009 is Free Will and Illusion. I found that really interesting. Kind of went a bit off topic, but this is why I included the last bit, because I thought it was very interesting. As always, this will be uploaded to YouTube, and you can subscribe, hit that little bell button, and you can watch at your own pace. Oh, Mary says, Nat, very interesting. I didn't realize there was so much to the brain. Thank you for giving me your time. No, thank you, Mary, for joining me. I love having people around, and the more we can learn about the brain, the more we can make informed decisions about ourselves. Our next webinar is the reward system. And you know how we always talk about dopamine being that feel-good chemical, that chemical that makes us, rewards us for being well-behaved. Let's go in a bit deeper on that. We've learned about when dopamine flows and when it doesn't flow, but let's learn about how it can be used to program us. So if you want to stick to a habit or not stick to a habit, if you want your body to function well, is there ways that we can kind of artificially kind of trick it to reward us? You might remember Pavlov's dog, where you ring the bell and the dog starts salivating because it knows food is coming. We're going to be looking a bit more into that, but from a neurological perspective. Oh, thanks, Emma. Appreciate it. Here's our contact details if you have any follow-up questions. My name's Nat, so it's just nat@exceptionalindividuals.com. Thanks again, everyone, for spending time with me today. Always great. And yeah, I'll catch you next week. Bye, everyone.